thank you for introduction. And the company name is Magellanici Space. We are an Estonian cybersecurity company focused on critical infrastructure. And now we are moving, I think, to the most practical panel during our event, because we'll talk about software development for Smallsat missions. As currently, well, we talk about security, we talk about policy component, but we need to remember that, well, we talk about all the things around the projects, and we need also to remember about the technical part, because in the end of the day, we talk about security strictly in the software and hardware components. And please welcome experts with who we will go through the whole software development process, its challenges, and also how the future of the cybersecurity for space industry will look like in next 5-10 years. Please welcome Kristo Allaje from ESTCube project. And Stefano Alberico from Skudo. Voila. Yeah, so I think that, well, we have also a small hero directly from ESTCube, and I think that, well, Kristo, you can tell something more about yourself and also about, well, one more panelist.
Okay. Yes, hello everyone. I'm Kristo Allaje, and I'm the current systems engineer in ESTCube. So we're a student organization supported by the University of Tartu and more directly Tartu Observatory. And we're focused on building the next big thing in space in Estonia, the ESTCube 2 student satellite. And I brought it here with me today, so you can have a sense of what it looks like. A lot of people think that, oh, you're building a satellite, oh yeah, it's like the size of a bus or a minivan or whatever. But actually the new things, the CubeSats, they're actually quite small. And the Estonian first satellite was actually even smaller. And this is the 3 times bigger here.
That's right, and well, we can say that we have even another speaker with Stefano. So, well, could you tell us more about yourself and also what you have?
Yeah, we both also together, some hardware to show. So, what could be inside that CubeSat, which is, let's say, is an encryption chip. So, provide cryptographic functionality. I've been basically working a bit more than 20 years, mostly in software development, and more recently with the hardware. And again, more recently with my company Skudo, we are basically focusing on securing digital communication, namely space communication, and which means using cryptographic components and algorithms to try to secure, again, the end-to-end communication. And not only about encryption, but a very important topic probably we will see is also about authenticating the endpoints. So there is a lot of work to do, especially in space application, because on Earth, let's say, most of this technology is widely used, very well known, applied, but in space there are still a lot of challenges. So to bring everything inside the CubeSat, it takes some time, and it is quite a challenge. So I guess we're going to analyze it.
That's right. So let's get direct to the whole process of software development. And how does it look in the space industry? Well, what kind of challenges do you observe from your experience, from making real life? Because, well, we talk about the most important thing when we talk about implementing the security into industry. So, well, Stefano, as you talked about, well, the component which can be used, I think that, well, we can start with this lowest.
Yeah, let's say software. So, one thing first thing comes in my mind, you develop software, right? So there is a lot of people have been developing software. There's a lot of companies that do software. And when it comes to develop software for let's say, space application, and for example, for launching on such CubeSat, one of the first things you could keep in mind, it's definitely challenging because, first of all, once the satellite is launched, you basically cannot touch it anymore. So there is, at least until Elon Musk will make it very, very cheap, you can't go there and do some fixing. So developing software requires a lot of testing, and I would say first design. So you need really to design it properly. And properly means, with, let's say, an engineering approach. There is actually, if you work with some project with ESA, so it's actually, I would say, very good approach, because there are certain, engineering documents to specify all the requirements and all the design. And there are, multitude of documents that actually you need to put together to start to design and build any software that then you want to send to space. So it's a challenge, and it's quite a difference probably from some other kind of software development that you have today. You know, imagine even there is a lot of startup that probably comes up with an application, a software app, and all they need to do is hit the market as soon as possible. So to do that, you basically throw it in the market, and the users will be testing your software. So you can afford to have bugs. How many times you are, you know, updating the application, whatever you have in your phone, even operating system. So probably every month you have an update on your operating system in the phone, and once in a while, any application you have is going to get an update. Now, when it comes to space, yes, we can update. Maybe we can talk also about this, but it's much more challenging because, for example, if you made a mistake, let's say in the communication module, probably Kristo then will show us, that means you probably cannot talk to your satellite anymore. So there's no way even to do any software update, and there is no way to send someone up there. So it is extremely important to design it and design every single component, I would say, properly. And then after design, yes, a lot of testing, like I said before. And when it comes to hardware, now, Kristo, of course, has the entire combination. Now, these are just, you know, chip, basically, that does encryption, and one of these basically is sitting inside a satellite. So we deal with, let's say, a subsystem, I would say a slice of that nice satellite. And but then when we need to integrate this hardware with the software, then again, there is a lot of testing. So you need to have a replica, for example, on your system, and you need to connect your hardware you are designing and try to reproduce exactly the environment you are going to have in space. And of course, you cannot reproduce the vacuum, but anyway, there are certain conditions you try to replicate, and hence you try to test your software and your hardware together in the ideal condition as close as possible to what will be the final, let's say, the end goal. So it's definitely different than, you know, probably a normal or more traditional, let's say, approach to developing any software for other domain. But I'm sure Kristo probably has.
That's right. And how does it look from your perspective, and also, you know, like managing the team of developers? So.
Well, maybe I'm a bit anticlimactic, but it's not really that different. Yeah. Like, yes, the biggest problem is that once you launch it, you can't really access it. But you still follow the same principle of you create the design, you create requirements, then you actually build it, and then you test, and you test some more.
And well, what about this testing?
Yes.
Testing scenario as well. How does it look like from your perspective, and also, you know, like what kind of things, well, should we implement in the whole testing process specifically for space applications?
Yeah, like I think the biggest thing is that you just decide upon a standard. It doesn't even need to be that good, but everybody just needs to be on the same agreement that that's how we do things, that's how the sequence and the flow goes, and then you just need to keep at it, because it makes everything less error prone. Like if you do your own thing and I do my own thing, and then we come together and you have this kind of an interface, that kind of interface, then it's going to create a lot of problems. But if we've already agreed upon that we do things this way, we pass these kinds of messages between the different systems or blocks that we have, then in the end, the thing is a lot easier, which is, again, like basically normal software development. But for some reason, a lot of people, especially students, because I have a lot of academic background, I lead students daily and supervise them. They're all like, oh no, space technology, and it's like super expensive, and like I'm gonna be touching a thing that's like gonna cost like $1 million or $2 million. I'm like, no, I'm not going to let you touch this thing. You're getting the small stuff first, definitely. Don't worry about it that much. It's not really that different. Yeah, and yeah, then once you actually do something, yes, you have your own tests to verify, but you should definitely run it on the actual hardware as well. A lot of students, again, especially like informatics, who haven't really done any hardware stuff, they're like, I run the same function twice, but it gives me the different output. Well, yes, because the sensor read different things. And they're always super surprised because so like traditionally you run the same piece of code, it has the same inputs, always the same outputs. But some people have a hard understand that you can't really replicate that with hardware. And yeah,
right. Yeah, and well, as Stefano already told about already deployed satellites, well, how does it look then? And how can we prepare the right update process So, well, I think it's also interesting case also that ESTCube will be launched next year. So
Yes.
I think that's the subject which is, I assume, very well discussed.
Yes, very well discussed, and a lot of sleepless nights have been discussed. Yeah, the biggest problem is that the slowness of it, I would say, and then the communication link. The fun fact with ESTCube 1 was that the communication system, if you sent a specific order of bytes, it always started crashing. So they had to do so many tricks and hacks to not send that specific byte string, because once you do it, you know that, oh no, now the satellite is like inoperable again. Oh no, what to do? So yes, the communications, the lifeline between you and the satellite needs to be like rock solid. And once you do the software updates, it's not going to be like usually 1 or 2 minutes. It's literally going to take days, if not a week even, depending on how much stuff do you want to send up there, because the data link is quite limited, especially for us as well, because we're using radio amateur frequencies and we can't really send a lot of data on there. And and then the packet losses and all that stuff adds up. Yeah, it needs to be very redundant for errors. You can't expect that whatever you send reaches there. It usually isn't there. Like on a good day, when it's high up there, most of the packets come there, but that's only once per day. Usually it's near the horizon, and basically half of, if not more, packets just get lost.
Yeah, so I think that you mentioned very important parts so about the planning. In
Yes.
fact, the whole hardware software integration, and also planning the whole architecture, even with more details and with more corner scenarios, I assume, in comparison to the typical software development that in space, we have a lot of different challenges. So I think that that's also the case with hardware. So, how can we ensure that the software quality and the hardware quality is good enough? So how can we test it?
Well, as I mentioned before, yes, you have to have a good standard. So like it was mentioned, at least follow one and usually the same way you develop software on the ground. So you need to have a good set of test cases that covers or try to cover, as much as possible, like we said before. So you cannot afford to, let's say, to forget some use cases, because otherwise you will not be able to fix anything, or it will become extremely complicated. So there is, a lot of effort and time spending in planning, definitely, this test cases. There is, in fact, test plan. There is, you do your test, you have a test results, and you probably keep iterating, because most of the time you find some test usually probably fails, at least at the beginning. And so iteration, it's your friend, I would say, to keep repeating and get them as exhaustive as possible. In our case, because it's I would say just a small part, so we have to focus at least just on these elements. But nevertheless, let's say when you do a CubeSat, you will have, you will iterate it probably more times what we do maybe on just one element. But I would say then it's a similar thing. So, and it's important, like Kristo was saying, to have exactly the same hardware. So of course you want to test everything on more or less the same board you are shipping into space, and that's why the reason that probably you build, more than one at the same time. Now, he's gonna have, this baby flying in a few months, so he's gonna probably get a lot of knowledge. In our case, actually, we are taking advantage of this program from ESA called the OPSAT. So there is basically already a flying satellite called OPSAT, and the satellite, lucky for us, has already installed. David actually is over there, so the responsible of this project. I remember last year was because we were announcing we are going to make it, so now it's happening. And so there is actually an FPGA chip, so there is similar chip to this one that we use. It's already installed in the satellite, so we don't need to fly there and do any change. And what we're going to do is basically remotely program this chip with our cryptographic functionality. And then we are going to basically test of course there will be some software, because you always need software at least to do a communication with the ground. And so we are going to basically have this space validation of this, cryptographic functionality that we develop here, we're going to get the space validation on board on the OPSAT. So program like that, for example, you have two two choices. Whether you build your own, let's say if you're a private company, most probably you need to build it yourself and pay for the launch, or get, let's say, a shared ride with someone. Or if you're lucky to be in the university, maybe university is sponsoring that kind of work. And but then in our case, for example, has been an excellent program to get access to, again, this OPSAT. So you have basically a laboratory flying around Earth, and you can upload your experiment and test it. So for industry, let's say, we are a company now here based in Estonia, is of course very important. If you want to do business in this sector, one of the first things they ask you, have you been flying your technology? So it's very hard to sell something if you cannot prove that it's working in space. So you would never buy a car if someone has never been driven it before. And so in space, and that's one of the challenge also for businesses, because the so-called sales cycle are much longer in space than on Earth. Again, you can build an app in a weekend and launch it on the market and probably start to make money, while for space you have to go through all these things and learn and do mistakes, because probably 90% of the stuff it's not written on any book. It's trial and error, and this is the second, I guess, mission. So ESTCube 2. So it takes a lot of time, and and so again, program like OPSAT for us are really, really very good. So,
and I think that you mentioned a very important thing regarding the whole process, that, well, it's complex. And especially in the industrial cases, we talk about cooperation with multiple companies. So we have very complex supply chain, both in terms of software and hardware, when a lot of different companies from different countries, even different regions, cooperate on developing the satellite of many different sizes. So what kind of challenges or threats do you see in this, especially that, I think it's a direct thing which touches the security of the hardware and software. And so what kind of challenges, threats, do you observe regarding the supply chain? So
I can start. Okay, that's for me, it's a very, very hot topic. Because it's been mentioned actually already in the panel previously, at least a couple of sentences I heard in this direction, also from the deputy from European Space Agency. So, cybersecurity, again, we want to protect, at the end you want to protect the communication. You want to protect your asset, which means you want to make sure that no one is taking control of this cube once it's up there. And that means you want to send, commands. You need to make sure that you are identified. So the right, let's say, operator send the commands, and the satellite recognize the operator almost by, a passport. So digital certificate, for example. So this is the software. When it goes to hardware, it's similar. If inside, the CubeSat, you have at the end, you need to have a cryptographic functionality that ensure the authentication of the user. So at the end, with traditional cryptography, you need to use a digital certificate. So that's your passport. And before the satellite, turn on an engine or change trajectory, you want to ensure that commands come from the designated operator and not from a rogue operator. So down, you will have a piece of hardware, and that goes to the supply chain. So how can you be sure that piece of hardware, even really this chip, hasn't some hidden functionality? This is now for me very topic. So if today you go on the market and you buy, let's say, this component technical called hardware security module, so HSM, which is the basic root of trust on top of which you can develop your cybersecurity solution. So how can you be sure that inside that chip, which is manufactured where? US, China, Russia, Japan. So how can you be sure that there is no, let's say, undocumented functionality, or let's call it backdoor? And it is, I would say, extremely difficult, not impossible to do it, but imagine really practically you should get, it's a piece of plastic, it's an ASIC chip, you need probably to delaminate, take a microscope, electronic microscope, go and read all the single millions of transistor basic connection that there are, reverse engineer every single functionality, and try to understand if there is something undocumented. So, as been mentioned already, probably it is very crucial in Europe, for example. We should rely on European-made technology, and this is one of them. So it's one of the building blocks. And so keeping an eye on the entire supply chain, it's fundamental, not only in hardware, also in software. As been mentioned in a panel before, what if your software, is outsourced and pieces are developed, you don't know where? Because nowadays it's very common to outsource, and maybe behind there is even, let's say, Indian company or whatever, without any negative accent. But so you need to make sure where it comes from. The same with food, nowadays I'm Italian, so you want to know where it comes from, that Parma ham, almost to the cow. And there is actually legislation, and European rules are going in that direction, so you can almost source and identify the cow. So you want to identify basically every single source of components of at least the most critical, if you want to have a, let's say, secure object. But maybe depends, of course, on the goal. Maybe for a CubeSat it's less
let's say
crucial.
that we're in ESTCube aren't as paranoid or don't have as much resources as Stefano has. But yes, I do agree that knowing where your things come from is quite important. As we're using open source or open frequencies, we can't really do a lot of decryption and stuff. But we have thought about how to prevent our satellite from taking commands from other potential threats, or somebody who wants to command it to, hey, turn on your engines or whatever from the other side of the Earth. So we have some cryptographic hashes and public-private keys on the satellite and on the ground station that the satellite uses to verify that yes, that command indeed came from us. But unfortunately, we don't really have any FPGAs or doing any authentication, but maybe that's a future collaboration
Absolutely.
We can have. Yes. So yes, we are interested as well in knowing where things come from and who did them, and can we actually trust these libraries that we find. But no, we're not going into that depth. If I would maybe have the manpower, I would, but that's not the focus currently on this project.
Yeah, so that's the plan for ESTCube 3.
Yes, the paranoid satellite. Yes.
Yeah, so, and I think it's also worth mentioning that also in terms of the legal, we talk more and more about software supply chains. So in fact, to build the whole immutable history of all made changes. So, and also, what is your perspective regarding, some legal regulations to force companies, both, private and public, to force them to build a kind of this, proof that everything what they use, was verified or is coming from the trusted third party. Well, what do you think also about this legal framework as well? You're more on this engineering side. I'm also mainly engineer, so it's always great to talk also about this legal framework. So, Stefano is...
Well, from what I can say, and again, having this cybersecurity as the main factor, at least for us, you can see that in certain application, maybe it's not important. It's more important to learn and develop new skills, and foster, let's say,
the main
education.
Point is just to build new engineering. Yeah,
it's education. At the end, it's a university project. You want to teach and
the core of the project is somewhere else.
Exactly, which makes sense. So when you say, security, cybersecurity, sometimes is not a priority, which makes sense. But some other time, it is very crucial. Now, going to the legal, of course, if we talk about, let's say, this aspect of the cybersecurity, so the let's say, encryption, authentication, cryptography, there is, of course, component that they are the certification. So this kind of technology are certified. So now the problem comes to, do you trust the certifier? Because in this kind of component, typically there is, let's say, US and European, at least the one that we consider in Europe. There are those two, so the FIPS and the common criteria. So there are two, let's say, methodology and certification body and certification process, which will test according to certain scene and use cases, test and then, certify you are a level, 1, 2, 3, 4. And that's the first building block. So, because again, this is, the root of trust is this most important components it's like your anchor in the boat. If you throw the anchor is holding all the rest. And so this is your anchor for all the security. So if you get this kind of certification, is one way of at least supporting, legally, let's say, your implementation. And but then the challenge really there, it's also, and I'm personally questioning, can I trust the FIPS, let's say, American model versus the common criteria? It gets very technical, but personally, I believe, like common criteria is testing a lot also the functionality and in a sort of more practical way, while the FIPS, it's a bit more, let's allow me the term, little bit more superficial on certain aspect. And but at the end you have to make a choice. So if your business needs to rely on something, then you, like you mentioned before, okay, you pick the standards and then you go along the way. So
yeah, and also at the European level we talk more and more about next generation of this security things. And one of the most hot topic, especially in the ESA level, is also all the things related to the quantum. So on the one hand, we have the quantum key distribution, which is very, very trendy nowadays. We have also the quantum computing. So how do you foresee the cybersecurity market regarding all of these quantum-related things, and how do you see the real use cases of this technology? Okay. And also, in which stage of this technology are we at this moment, as we talk a lot about quantum-related things? So
Okay. Well, yeah, quantum computing, it's a big buzzword. I'm still on the FPGA buzzword, finding programmers for that. But as much as I've heard, not really an expert, unfortunately, it's good for simulations and all that theoretical things. But when are we actually going to get this quantum cryptography breakthrough and all that stuff? I think it's like still years away. But yes, we should definitely look into like quantum computing resistant algorithm stuff. But I'm saying that I'm going to deal with it when it comes to there. Maybe not the best approach, but
no, I mean, it's again, what's your goal, right?
What's the goal of
the different use cases?
Yes, for me, it's not really that important, the quantum computing part. Like, I mean, maybe ESTCube will have a quantum computer on it, but maybe not.
Yeah, well, okay, that's you put together quite a lot of stuff. So let's start this way. Again, for me, it's a very crucial aspect, because everyone is talking about quantum computing and post-quantum cryptography. And let me start to say that, so to protect the data with some sort of cryptography, it's a mathematical problem, okay, so just to make it very clear. Now, quantum computer comes, and what they promise is they are going to execute certain algorithm in a, let's say, speed, which is much, much higher than any computer we know, based on traditional electronics, let's say. And so there are certain cryptographic functionality which are, I would say, weaker to quantum cryptography, so quantum computing. And those are specifically the one that are dealing with the digital signature and digital verification. So there is this is actually first things to really separate. So the pure so-called symmetric cryptography, the pure encryption, is probably going to be quite safe. Some researchers are saying maybe you just need to double the key length, but you can still keep using the same algorithm. And I'm referring, for example, AES, maybe some of the people know. So that part of pure cryptography should, let's say, survive. But when it comes to let's say, do a digital signature, so which is all what you need to authenticate, your endpoint, then you need to come up with something else, because most probably quantum computers are going to break those parts. But then what happened is quite interesting. It's like the cat and mouse. So at the same time, they are inventing quantum computing. At the same time, they are inventing quantum-resistant computing. So what does it mean? They basically develop new algorithms which cannot be broken very easily by the quantum computer. And so what happened is there is a NIST competition, so the American National Institute of Standard and Technology, which is going on for a few years. And now we have just recently, I think a couple of months, started around 4, and we have some sort of winners which will become standards. Winners of what means? I mean, there is a family or set of algorithm, quantum-resistant algorithm, which will probably resist to quantum computers. So what we can do today, yes, we build this using, now we have to use the term traditional cryptography versus quantum-resistant cryptography. So from my point of view, I have a chip that I can program and I put on a satellite. And now today, maybe my algorithms are traditional cryptography, but then we can have a migration path because I'm able to reprogram the chip, replace the broken, let's say, algorithm, and put the quantum-resistant algorithm. So in a way, this is, as I see it, it's going to move. ESA, I've seen they are actually supporting this kind of use case, or they talk about hybrid solution. So when you start with one technology and then be ready to move to the next one. But there is one thing also to keep in mind that, so there is this competition. We have a set of candidates. I don't remember, it was 7, 9 at the end. But I think it was in February, there was the news that one of the finalists, and we are on the 3rd round this year, so it's been going on for a few years, try to find this new algorithm, new quantum-resistant algorithm. And there was one of them, I think it was Rainbow, in February, that came up a paper saying, I don't remember the exact title, but something like, you can break the rainbow with a laptop in a weekend. And that, of course, was like, whoa. And then has been verified, so this is actually true. Of course, it's, let's say, there are different levels of security within a single algorithm, and so let's say the lowest level has been compromised, so this attack was actually successful. But now the important in all this, I would like to say, it's to draw your attention that this is very new technology. I mean, quantum-resistant quantum computing. So we can still make mistakes. You see, we spend years on the NIST to try to find the best. And when we were on the final, the final basically was now in June, suddenly one of them failed and he was passing already all the tests. So you need to make you think these things are complex. And especially in cryptography, you can't invent something, super secure in not in a month, not in a year, and probably not in a few years. So this technology needs to mature. And to close it again, because it's a very complex aspect, but to close, there is a big elephant in the room as well, that when you deal with the, let's say, space and data protocol, now it starts to get a bit technical, but you want to follow standards, right? So you cannot reinvent something on your own, especially when it comes to cryptography. So now standards for space mission, now I have my view probably limited, so I'm not an expert on all of them, but I can see that at least the one that we are using and widely used under the CCSDS umbrella. So one of the standards for encrypting the communication doesn't even support a digital certificate. So there is no concept of digital certificate in there. What does it mean? That, and this is what happens in the reality, you are preloading your encryption keys on a satellite enough to support your 20 years mission. And then you use those encryption keys, and from ground, you say, through this protocol, you say, now use key number 1. Then after you are happy, up to you, up to the operator, say, let's now switch to key number 2, key number 3. So you are consuming the keys. And this is as a, one main problem. It works, you can use, and we are talking only about encryption, by the way. We are not talking about authenticating. So there's nothing related to say, is it really that satellite I'm talking to, and vice versa. So this is not possible because the protocol doesn't support it. But now imagine you lose the keys on the ground, you lose, let's say, they get compromised, right? Someone is making a copy of your keys on the ground. Your entire mission is gone. Like there is no more security because there is no way to update securely a new bunch of keys. Why there is no way of updating? Because you don't have authentication. Let's say by authentication, I mean strong authentication of the endpoints based on digital certificate. Because if I would have that one in there, then I can upload new keys. I can upload new software. You mentioned updates. So to do an update of a very critical functionality, the building blocks that you need is this authentication. Otherwise, how you can ensure that your software that now you change and you upload, how you can make sure it comes from you and not from me, a rogue operator. So anyway, it's a long excursus, but with the quantum cryptography, let's say to summarize, is there, it's coming. Someone before, I don't know, Dan Bogdanov says, in some room somewhere in the world, probably they are more advanced than us, and I believe. This stuff, I truly believe it's going to come first from military, so we are not going to hear for sure for a while, because whoever comes with that capability to break keys is not going to advertise it, it's going to exploit it. It has happened in the past, and it will happen again. So they will exploit this until probably they cannot keep the secret anymore, and then it will become public. So somewhere this capability is there. I think it still takes some time, because I still have to see publicly really some useful implementation of quantum computing capability, but it's very promising. So at the same time, like we were saying already, you need to be ready to move on, migrate, have your system capable of, with let's say this nice word, hybrid solution needs to be able to be future-proof. So today you are ready for traditional cryptography, tomorrow you are ready for quantum resistance and beyond. Mm-hmm. Because, by the way, there are even algorithms which are already today secure. They are called information theory secure, ITS. So there is mathematical proof that those algorithms cannot be broken by any computer. So they're already today available. So anyway, plenty of technology that can be used.
Right, and well, you talked about very important aspects, so about the new technology, so that we talk about some research in this area. And well, when can we use the phrase that the software or hardware is mature enough to implement it in our space asset, especially that, well, we talk a lot of about research. And well, when can we use this phrase that, well, it's mature enough to implement it? And how do you see also, methods or approach to speed up the development of many of new technologies? Because I think that's one of the most unique things regarding the space infrastructure and space assets, that the technology must be verified and proved. It's not like with software as a service, but when we can easily migrate to different solutions, and well, that's all. And when can we use the phrase that the technology is mature enough?
Yeah, I do agree.
Yeah,
that,
it's like philosophical questions. So.
Yeah, very philosophical. Like, I do agree that the space industry is quite behind current trends. Yes, a lot of standards that they have used are ancient, I would say. Especially the protocols that we're using with radio amateurs again. I don't think I was even born when the draft that I'm still following came out. But I need to use it because that's the standard. But yeah, something that works and they just keep on it. But luckily with the newer CubeSat things, you can test new things. The cost of failure is a lot cheaper than the conventional millions and millions that you usually pay for it. So I think the iterating will start increasing. And I think after a few missions, you can already bring it hey, it's been flight proven, it has a track record already, it's mature enough. But again, depending on what you're doing, maturity, I would think that's a lot of it depends on what you're doing. For us, okay, it works on the ground, I guess it's mature enough to go into space now. But again, we're a different use case. It's not really that expensive. It's just for academic purposes. The entire point is to gain knowledge. So I guess we're the risk takers here, the bold ones. But yes, I do agree that if you're sending up a GPS satellite or some telescopic satellite and you literally have paid millions and millions for it, then the term mature might need that, yes, 1960, maybe that's actually too new. Let's go further back.
Well, how does it look like from
one point it touched, it was very, very interesting, because what this kind of gadget allows us is really to make mistake in an affordable way. Yes. Probably think back, I don't know, 20 years, how much, was the cost of launching anything in space, and then you cannot afford it. That's why today, actually, some of the standards, we are following for developing software are so rigorous, because you couldn't afford to make mistakes, and those standards come from some years back. So now probably you have the luxury to really, trial and error. I mean, especially if you're at a university and you are, supported in this way, I think that's a very, very big advantage. So they are extremely cheap compared to what used to be. and hence probably the need for a mature technology probably become much less, because you can afford to say, okay,
it's
works.
not that costly to fail. It's
Exactly.
like, yeah, whatever. So it failed. Let's build another one. We have another copy on the shelf.
And that's, I think, you can take advantage. So you are at the end, you are learning. You need to learn. You need to educate more people, and this is now more affordable, let's say, way of educating people. And I think 20 years ago we couldn't do something like this.
Right. Yeah. So I think that we reached our last important milestone. So now it's time for questions and answers. So are there any questions?
Hopefully we didn't scare everyone off.
Hello. Test 1 1 2. Hello, this is Pritan from Guard Time. We talked a lot about software development and the challenges and the solutions there. Can you elaborate also a little bit about the possibility to go to the market with your excellent solutions? Like for the Smallsati missions, you develop, put it together, it's tested in space. How easy or hard it is to start making money with that solution? Thank you.
Okay. I mean, if you have a person who is willing to put into the effort, then yes. Like the ESTCube 2 platform has been designed to be kind of quote-unquote marketable, that we designed the satellite itself. We have all of the things. We have shown that, hey, it made a beep, and we have a lot of space, so give us money and we will put your experiments on the cargo ship. But I think it's just effort and time, nothing else, like with everything. But the person with that.
Yeah, maybe like I was touching a bit before, but like I mentioned, this long sales cycle. So because you need to test in space, otherwise no one is going to buy your technology. That's already the first quite hurdle, I would say. Now, like you mentioned, you need probably to iterate 1, 2, 3 times to say you are mature enough and your product is solid enough to be sold.
You need to prove it.
Yeah, you need to prove it. That's one thing in space they ask you. So you can develop any software you want, but for space application, really the first question from a customer is, what's your heritage? How many times you have been flying, and show me, because you can basically track any mission and you can prove, and you need to prove basically you have been in space. So from business, pure point of business, let's say the question is, I would say a bit more challenging. It takes more time. Difficulties is probably similar, like he was saying, before. It's probably the same as developing a software here, but definitely will take longer time. And if you can probably access someone already experienced, I would say you probably can save some time. But if you start from scratch, you have to plan for some, possibly failure, but anyway, some time that you need to invest because you are going in an environment that you don't know at all. And so... Yeah.
It's easier for somebody to say, hey, like, I think it's a bad idea because of otherwise you're going to just make this bad experience yourself. And like, oh, yeah.
Well,
yeah.
Hopefully it answered the question.
Yes.
Are there any more questions? If not, I think that we can finish our panel. So now it's time for a big applause for our great speakers.
Yes. Thank you.
Thank you. Okay.
And the last information, when is it scheduled to launch the ESTCube?
Yes, the current plan is January 20, but as with all space tech, it will probably get delayed, but definitely next year.
That's
right. It's easy to say. For us as well, next year, but it's going to be February probably.
That's right, with Artemis and all the space projects.
There's still one Vega C before us, so that will probably be delayed, and that will delay us and all that stuff. Good.
Oh, yeah.
Great. Well, thank you for your attention, and
thank you.
See you during ESTCube launch.
Yep.